Okay, all right, now we start getting to the fun stuff. So performance analysis. So far you've been running your program and pretty much only care if it completes with the correct answer or not. In this class, the performance of your application will be tested and graded accordingly. Performance does matter in computer science for at least a certain threshold. For certain programs, it doesn't matter as much as others. For example, your app, if it has a slight lag to it, your user might be annoyed, but people will probably still pay for it. On the other hand, if your program needs to keep someone's heart beating or something along those lines, the performance is actually literally vital. So we're going to come up with different tools to actually analyze the performance. But for this course, we're only going to start with the basics. We're not going to get too much into all the details because that requires a thorough understanding of computer architecture. But we're going to do it both empirically, which means we're going to run the program and get timing information, and we're going to do it theoretically using something we call big O analysis, which is a very useful tool for saying when one program is faster than another. Okay, so what's the usual dilemma here? You have two or more methods to solve a problem. How do you choose the best one? Well, hopefully most of us would think, okay, let's just write it in C or whatever and test how long each one runs, which is not necessarily a bad way to go about it, but there are some significant issues with it. First off, you may have different implementations. My implementation may run better than your implementation or vice versa. Some algorithms run faster on some computers. This is actually a very interesting problem when you go to architecture, because your algorithm may run very well on this machine, but not very well on the machine next door. And that can cause, that would make your analysis incorrect. Algorithms may perform differently on data. So with one set of data, your program runs faster than the other one, but on a different set of data, your program runs slower than the other one. So how do you know which one is actually best? So the point is, doing it empirically is not necessarily the best. The first thing you want to do actually is apply at least a basic theoretical analysis, which we will get to. So a better approach is think of it theoretically. So think of it as a characteristic of the key operations. For example, sorting, you really want to know how many times two values are compared and swapped, because those are the two main operations inside of sorting. What? Search, count the number of times they're being compared, because that's what's inside of search. Recursive functions, in general, you want to count the number of recursive calls. So a better analysis is to, hey, let's go look at what is the key operation and then do analysis of those. Another thing, keep in mind, you want to think of general performance, aka as the data inputs become large, what is going to be the behavior of the program. You could try and measure it empirically, but does that really tell us in general? Well, maybe, maybe not. Well, that'll make a lot more sense later on. You may have to get a really large number before you can figure out what the graph looks like. So an analytical, or theoretical as I called it, access performance and abstract. So you're thinking of the program as an abstract process, and how fast do you think it would run on any computer. So for example, sorting, how many comparisons for an array of size n? So given a size n array, how many comparisons do you do? Searching, how many comparisons again for a size n? Sorting may also be how many swaps do you do with a given array of size n? Last bullet point, sometimes it may be difficult to discover a reasonable formula, but hopefully for this class you'll at least be able to come up with the basics. Let's see. Oh, last thing before we get into it. Sorting algorithm routine may require n-1 comparisons, or as many as n squared over 2. Hopefully you can tell by just those two values that the n-1 is superior to n squared comparisons. Does that make sense? Because if it takes n-1, then if you have 100, it takes 99. But if you have n squared over 2, it takes 100 squared, whatever that is, 10,000 divided by 2, so 5,000, which is significantly more. Types of analysis, because your program may behave differently with different data inputs. So we usually look at best case, average case, and worst case. What's the best it can do? Well, some programs they just do a quick check, is it already correct? Okay, then exit. All right, well, that'd be your best case. The answer was already provided. AKA, it was already sorted when you gave it to me, so I'll just exit. Average case, how fast does it run on a given random problem of size n? And then worst case, what is the worst path along here that can happen? We usually deal with the worst case. Why do we usually deal with worst case? Usually. I'm sorry, go ahead.
The longest it will take, and if you want to know what the worst possible scenario for your user is, that'll be how long it will take.
So, okay, so it gives you the worst. It's giving you a bound. It's basically guaranteeing you that your program will not go slower than this. And that's what's nice about worst case. When would you not use worst case? We are going to go over one algorithm where we don't use
Trying to do
worst
something
case.
for yourself.
Trying to do something for yourself. Okay, why? All right, why would you care about worst case in that situation?
Because you know your setup.
You know
you're gonna be faster than.
Okay, you know your setup already. Okay. Yes.
And you're dealing with a really, really small data set.
Really small data set. Okay.
Generally, if it's like under 50
Oh, yeah.
values, because then it doesn't really matter between the algorithms.
Okay.
It makes a slight difference, not much.
Hmm?
At this point in time, I guess.
Yeah.
Most hardware can run it if it's a small data set. Then once you scale it.
Yeah, then-
It should be changed.
That's-
You should say, what is the longest an algorithm can run for a problem besides in before somebody gets angry. That's really what you want to know.
That is what you want to know. That's correct. That's correct. But this is objective. Before someone gets angry is subjective. So we're going to stay objective here, Tyler. Good point, though. Good point. Good point. So, in general, we will use average case. I kind of came up with some decent ideas here. A lot of times, if the worst case is very, very rare, which does happen in certain algorithms, we'll stick with the average case, especially if you're applying to the algorithm to something that's non-vital, like again, a phone app. Then you probably average case is going to be okay. Again, if it's a health program, you're going to want to stick with worst case. In general, we don't care about best case. So just go ahead and throw that one out, but we will talk about it. Okay, we are going to be estimating. Analysis or theoretical analysis or analytical in this case is an estimation. It's an important skill because it'll help you quickly determine if one algorithm is better than another. So here's an example question. How many hot dogs tall is the Empire State Building? A lot. Great.
Depends on how many hot dogs are.
I mean, what?
You got a foot long hot dog, you got, ballpark
Okay,
frame.
good. Yeah, so we need to start, so it's 6 inches per hot dog.
Because I know how many feet tall, I can figure out how many feet tall it is.
Okay. Okay, there we go.
Then you just convert it.
See, all right, so we already know how to estimate. This is great. All right, so yeah. How tall is the Empire State Building? 1,250 feet tall. At least that's when I looked it up. If it's 6 inches from end to end, you would need roughly 2,500 hot dogs. If you actually did the hot dogs and did this empirically, would it be exactly 2,500? No, but would you expect it to be fairly close? Yeah.
Within 5.
Within 5. Right. Okay. So, right. All right. So we are estimating, which gives us an approximation that is actually very useful. Okay. So the first thing we're going to talk about is complexity analysis, which is going to look very, very horrendous, and then we're going to use big O, which is going to make all our lives easier. Got it? Good. So it's an objective way to evaluate programs. It's computed in terms of space or time. Space being memory usage, time being amount of time it takes to complete. Remember, some programs have limited memory, so it's important to at least account for memory. The goal is to have a meaningful way to compare algorithms. It has 2 phases, algorithm and, of course, complexity analysis. All right. Algorithm. Usually apply a set of rules to be counted. Bullet number 2 is the sad face. There are no generally accepted set of rules for algorithm analysis. Sorry, guys. I'm going to at least give you what I believe they should be, and then we'll just stick with that. If you stick with those, you should be pretty good for most of the time. In some cases, exact count of operations desired. In others, a general approximation is sufficient. And by in others, I mean most of the time, a general approximation is sufficient. And the rules presented are what I consider. Rule number 1 for this class, we are going to assume an arbitrary time unit. 1. How long does 1 take? I don't care. We're just going to say it takes 1 time unit. Okay? You can pick nanoseconds if you want to, whatever. Okay. Execution of one of the following takes time unit 1. Assignment, I/O, Boolean, arithmetic, function return, array index, pointer dereferences. Is that actually true? Do all these take the same amount of time? No. Keep that in mind. We're assuming they do, but they definitely do not. But to make our lives easier, because again we're approximating, we're just going to assume they take time unit 1. Example. Hey, we've got a line of code. Count equals count plus 1. And we're going to say that line of code has a cost of C1. Sum equals sum plus count. We're going to say that has a cost of C2. Total cost, of course, is C1 plus C2 because that's the cost of the 2 lines of code. We assume addition costs 1 and assignment costs 1, so the total is 4. Why is that?
2 additions and 2 assignments.
Yep, 2 additions, 2 assignments, that sums up to 4. All right. Everyone see what I'm doing here? Any questions? Because it's going to get more confusing when we start with the basic example.
Then why does the comment on the first line say cost C1?
Because that's the cost of C1, which is the first line. So that's C1 referring to the addition and the assignment. So the cost of C1 is actually 2.
Oh, I see. That's the lines.
Yeah, it's a line. It's that exact line. All right, some more rules. If switch statements, you want to take the time of the condition evaluation, because there might be a lot of conditional evaluation there. You know, add, not add. Well, there might be an add, actually. Add, and, or. And then you want to add the max of the running time for the individual clauses, because in general we care about the worst case. So look at all the clauses, you know, if or else, or if it's a switch statement, every single case. Whichever one takes the max, you want to add that to the condition evaluation. That will give you the total cost of the if and switch. Okay. Loops. Time for the setup. In, where in is the number of times the loop is executed. Of the body plus the iteration expression. Remember your for loop, that last expression is what's actually called. And then it's plus in plus 1 times time of the loop condition. Why does the loop condition get an extra 1?
You have a lot more than
Is it because at the end you evaluated the one last time since it's false?
Exactly. Yeah. So remember at the end of in, it does evaluate the condition 1 more time before it exits the loop. So it's actually in plus 1 for the loop condition. Rules make sense? We're about ready to do examples. Somewhat? All right. Okay. Here we go. Cost of C1 is 1 because we're just doing a less than. C2, the cost is 2. Why is the cost 2 there?
Assignment and I guess the negative is an operation.
Yeah, negation. Right. The negative or the negations operations. That's 2. C3 is 1. So your worst case is 3, because if it is taken, then you're doing 2 more operations and then you get out. Best case is 2, and we'll just say the average is 2.5. When you do average, there's a lot of kind of hand waving going on, because I'm just assuming that both clauses are executed equally, which may or may not be the case. Everyone good with this one?
Wait, why is it 0.5?
Because if I were to, assuming that each clause was executed equal number of times, and I ran it, 1,000,000 times, and then I averaged it, it'd be 2.5. Because the first one is 3, the second one is 2. So. All right, here we go. Hey, how about this? Now we're going to start doing it ourselves. What's the cost of C1? 1. Cost of C2? Okay, also 1 and 3. So I'm going to go ahead and give you those. Less than or equal is actually one operation inside the architecture. What's the cost of C4? And the cost of C5? Cost of C5 is, where's the third one? I only see 2. Okay. How are we going to do this loop? Well, go ahead and look at it. Cost of C5 is 2. Oh, yeah. How many times does a loop execute? Yeah, so n hasn't been defined. I haven't showed you what n is. That's part of the problem. It does it n times, right? Yeah. It's going to execute it n times. So the total cost, here's the formula. C1 plus C2, right up here. N plus 1 times C3, because that's the conditional, plus n times C4, because C4 is going to be run n times. N times C5, again, run n times. You go ahead and you math that out real quick, and it comes up with this formula. Yes?
Back to plus minus.
Oh, sorry.
Cost of C5. How did you get 2? I equals 1. Oh,
You have one addition, one assignment. Now, we don't care that it may have cost 2 to get I or something. Just to do the addition cost 1, do the assignment cost 1. Okay. Good question. Any others? All right.
All right.
Yes.
The n plus 1, can you explain that again when you're looking at that?
Sure. So, if you let's say n is 3 to keep our lives easy. All right. So I is 1. So I equals, we'll start with 1, and n we said 3, right? So it's going to first test is 3 less than or equal to, 1 is less than or equal to 3, right? So that's the first run. Next time it's going to increment I to 2. Is 2 less than or equal to 3? Right, so it's going to test that. I will equal 3. Is 3 less than or equal to 3? Correct, so it tests that. Now, when it goes to exit, there's this last test. Is 4 less than or equal to 3? No, but that was a test, and that is a cost. So it cost 4 times, even though n was 3. It's always going to cost 1 extra time because it has to do that last conditional evaluation. Any other questions? Go ahead. That's fine.
How does that factor to the total cost?
I'm sorry, used a pronoun. Which that?
What's that?
Used a pronoun. Which of that are you referring to? Which?
The last line. Total cost of C1.
Okay, so C1, you only execute C1 once, correct? You only execute C2 once, correct? We end up executing C3 in minus 1 times because that's conditional of the loop, right? We execute C4 n times because that loop's body is executed 4 times. C5 is executed n times because, again, it's inside the body, or if it was a for loop, it would have been the post-iteration statement. So we execute that n times as well.
Okay.
And now that we have math, we just multiply it out and call it a day. I just simplified it this way. What's that? Okay. Anything else? That's great. Thank you for asking questions. Last class didn't. They had many problems with this.
Why is C3 on both insides and C1 and 2 on the outside?
Remember, it's n plus 1, so you get one of them out there, and then you would then have n times 3, C4, and C5. So I was just showing that there's an n, and then there's this in front of it. I'm just simplified it this guy. Okay? Yeah, it looks on both. But in reality, what this is constant plus basically constant times n. And I put in this formula because that's going to be very important when we go to big O analysis. Okay? Any other questions? I'm about ready to take this to the next step. All right, here we go. Well, you have a loop inside a loop. Y'all have written loops inside of loops, right? Yes. Please say yes. What?
Everyone's so good.
That can't be new, okay? All right. Okay, so hopefully the costs, the individual cost, should be at least somewhat straightforward. Let's see, 1 is 1, C2 is 1, C3 is 1, C4 is, of course, 1, C5 is of course 1. C6, you have an addition and assignment, so it's 2. C7, addition and assignment, so it's 2. C8's addition and assignment. Okay. Anyone want to take a guess on how we're going to do this?
Lots of math.
Lots of math. Nice.
Would it be like 1 plus 2 plus 3 times n plus 1, and then the inside?
Okay, let's start from the beginning. First, consider the outer loop. The outer loop executes n times, right? All right, so we can just, all right, outer loop.
N times C4.
Yeah, so yeah, n times C4, n times C8, right? All right, but C5 is going to be a little different. The second loop also executes n times. All right, that's the first thing to keep in mind. How many times do each of these loops execute? The while loop inside is n times, and the other while loop is also n times. So total cost, oh boy.
This will be n times n.
So this can be a little hard to recognize. We're going to go ahead and step through this real quick so you see how this is formulated. Like I said, this is going to cause some sadness, then we're going to go big O, and you're going to be happy.
Okay.
All right, got it?
As long as the test is true.
Oh yes, you will like big O. All right, let me go use my mouse pointer for the people online, or people who are viewing the video. Okay, C1 plus C2, those are executed once. Everyone good? All right. N plus 1 times C3. That's because this C3 is only executed N plus 1 times. It's on the outer loop, right? All right, got that knocked out. Great. N times C4, obviously he's on right there. That's how many times he's executed. Now, how many times is C5 executed? Well, it's N times for the outer loop, but each of the outer loop he's executed N plus 1 times because the inner he's the conditional for the inner loop. So, yes.
And these n's can be 2 different values.
They could be. I could have had N and M, but in this case they're both N, which is going to be very common for a lot of algorithms. So N times N plus 1 times C5. All right, great. We've knocked out C5. Well, actually, C6 actually should start becoming pretty obvious because inside of this loop it's executed N times, and this loop is executed N times itself. So C6 is just N times N, or N squared. Y'all see that? Same thing with C7. And then keep in mind that C8 is inside the outer loop, so he's only executed N times. We do some math, come up with that formula. I'm putting in this term in this format, so you see that it's really constant plus a constant times N plus another constant times N squared. Okay, everyone see what I did here? Yes.
The n squared part, I didn't understand.
Okay, let's look at C6. I think that's going to be the easiest way to evaluate this. How many times is this loop, how many times is C6, executed inside of this loop? N times, okay. How many times is this loop executed? N, or just N, right, because of the outer loop. So it's executed N times inside the loop. The loop itself is executed N times. So that means that C6 is executed N times N. Okay? Oh, yes. Go ahead and leave that note up there. You're good?
Yeah, it wasn't a question.
Okay. Notice N squared is the highest term. Can anyone guess why we care about that?
Yes.
Why?
The higher the term, the longer it takes.
Yeah, the longer it's going to take. Okay. Well, the word that we're going to come into use is that it's the dominating factor, which is what Big O is actually about. All right, so I talked about complexity analysis pretty specifically. We are going to now make it easy for you. Or I'm going to make it easier for you. It won't be easy, it'll just be easier. All right. We like to measure an algorithm's time required as a function of its size. So that's why I've been using N in our previous examples, because usually you have some size. We like to call it N. That's just what we call it. Afterwards, we'll call it M, because we're very unoriginal, I guess. So problem size may depend on application, number of elements in the list for sorting, or maybe the number of disks in the Tower of Hanai problem. So if we say the problem is N, algorithm A requires 5 times N squared time units to solve. a problem of size n. Algorithm B requires 7 times n timing to solve a problem of size n. Which one's better?
Depends on it.
Depends on your input. But which one would we, if we were just coding it for general, which one would we choose? B, right, yeah. So it depends on the size, but in general, as n becomes big, B is always going to become more important. All right, we call it the growth rate. We compare the efficiency algorithms by comparing their growth rates. All right, let's look at another one. So which one of these two is better? Look carefully.
Oh, no. Yeah. First one.
First one.
It depends on n again. Right. All right, well, let's go look at it.
Well, 3 to the end is never good. 3 to the end is never a good thing.
I'm glad I touched that in OP. 3 to the end, yeah, give up all hope. All right, anyways. So for n value 1, well, actually the second one, 3 to n is doing great. So 2, 3, 4, 5, 6, 7 even. Oh, and then 8 is when it changes. And then 9, oh wait, and then 10, this is by order of magnitude. If I were to keep going, which one's going to win? The first one. All right.
Well, I guess if it's less than 7, it's less than 7.
Yeah. Okay, so the question is, what's going on here? Why is this happening? We have these kind of gross formulas. Well, maybe not too gross, but they're longer than what we'd like to deal with. So I'm giving you a picture of the second one with the 3 to the n. On the first column first one's n, the size of n. The next column is the value of the entire formula. The third column is just the term 4 times 3 to the n. And then the final column is the percentage that term 4 times 3 to the n is basically consuming of the total. All right? So as n becomes large, notice what happens to how much of the number is really the 4 times 3 to the n. More and more and more until it becomes practically all of it.
My n's the end cut on this video.
Yeah, you don't want that, no. Don't want that, don't want that.
Anything's the end is a no-go.
All right, so here's what it comes down to. Notice that one term dominates the others. That 3 to the n is really dominating the rest of the terms. So in reality, or this implies, I should say, we really only care about the dominating or the highest term. So we can say one's n squared and the other is an n algorithm. Obviously, we care more about n because if n becomes anything useful in size, the n algorithm is going to be faster. Okay. So here we go. Give you a quick ordering. Log base 2 of n. Actually, that's pretty nice. Yeah, n, it really doesn't grow that fast as n becomes large, even exponentially large. Notice that's kind of the graph. Well, we'll get there, n grows directly, all right. N times log of n is actually not that bad. It's, n is faster, but n log n is definitely slower. N squared is where things start to really slow down, although if you think about it, 10 to the 10, what is that? 10 billion? Did I get that right? Yeah, 10 billion for 100,000. You know, you throw a supercomputer on it, you should expect that to happen, right? You can do it. Actually, maybe even our machines could get it done in a couple of days or a week, right? If it was a really important problem, we could do it. I mean, before then, in log n, yeah, our machines could do it fairly quickly. Low values of n squared, not too bad. N cubed, it does grow somewhat faster, but again, 10 to the 15th, a supercomputer can probably knock that out in a few hours, right? In other words, we could still use that algorithm and come up with a solution within a meaningful amount of time. All right, let's look at 2 to the n. All right, 10, all right, let's find 10 to the 30th. Oh, wait a minute. Supercomputer probably, yes, so n's 100. 10 to the 301. It's not going to happen. Well, you better be really patient. And have lots and lots of money.
How about with coffee?
And then, but that's only n of 1,000 elements, right? I mean, a lot of problems are going to have more than 1,000 in. 10,000? Wait a minute.
Lost it. We're gone.
100,000? Yeah.
We lost it.
Don't even try.
Goodbye, TIA.
I'll use my TI-83 real quick, guys. Got it. Got it. Okay. So the point here is that if you have, really the point is, once you see 2 to the n, just give up. Find something else. Don't. It's not gonna happen, unless n is really small. Unless n is small, but that's not usually the case. You'll go more into that when you take algorithms about what's going on here, but or basic math. But anyways, yeah, 2 to the n, not gonna happen. Of course, 2 to the n is less than 3 to the n, et cetera, et cetera. This can keep going. So there is actually an ordering here. Hmm? Yeah, no. Don't do it. All right. So because of this, big O is going to help us out and simplify our problems. So I'm going to first give you the complex definition, and then I'm going to tell you what everyone else in the world does, which is not this. Well, it's similar, but first off, understand that if algorithm A requires time proportional to f of n, A is said to be of order of f of n and is denoted O of f of n. So O is going to be a notation that computer scientists use, big O. The function f of n is called the great root function. Since capital O is used in the notation, this notation is often called big O notation. So if A requires time proportional to n squared, it's called O of n squared. That should be a squared, out of 2. If it's proportional to n, it's O of n. How do we actually do this mathematically? You haven't taken discrete math yet, so I'm not going to require this of you, but let's go look at it real fast. If an algorithm requires n squared minus 3n plus n seconds to solve, if there exists a constant k and n0 such that k times n squared plus n naught, or n sub 0, is greater than the actual function for all n and 0, then the algorithm's order n squared. And in fact, if you plug in k is 3 and n0 or n naught is 2, this holds. Thus, it requires no more than k times n squared time units, so we just say it's O of n squared. All right, for those of you who didn't get it, that's okay. It's actually not that difficult. It's a game of spot the highest term. That's all you're doing. So on the left, you have 50 n squared plus 31 n cubed plus 24n plus 15, which is just O of n cubed. Hey, look, we just found the highest term and then wrote it on the right.
Yeah, like that.
Is that easier? Yeah. Okay. Same thing with the next one, O of 3 to the n. Keep in mind, this can get tricky. Why is the last one O of n cubed, even though there's no n cubed written there? Yeah, you do have to multiply it out and simplify it to terms. Same thing with the next one. Because in the next one, notice you have log of n times n. When you multiply that out, you're going to have a term that's n times log n. So keep that in mind when you start evaluating. All right, so that's big O. You should be using this all the time. And we will be using this in this class. Oops. Okay. Quickly, before I stop the recording, let's go talk about the different growth rates. O of 1, sorry. The time requirement is constant and it's independent of the problem size. So even if you gave it a size of 1,000,000, it just takes a constant amount to give you an answer. We like those algorithms. They just don't usually happen. This would be like you have an array and you have an object array and that keeps track of the array and the size, and you want to know its size, well, you just return that value, O of 1. So that'd be an O of 1 algorithm. Log n, time requirement is logarithmic, increases very slowly as the problem size increases. We like those. Those are very good. O of n is a linear algorithm, increases directly. N log n is basically it's an n log n relationship. When you start experiencing these algorithms, you'll see the difference between n and n log n and n squared. It's more rapid than linear, but still significantly less than the next one that we have listed here, which is quadratic. Increases rapidly. N cubed also increases quadratically. And this is really the best one. O of 2 to the n. The time requirement is too rapid to be practical, is really what it comes down to. AKA, just give up. There are other ones, like n to the 4th, or square root of n. Actually, where would n to the 4th fit in this? N cubed n, yeah, 2 to the n. Where would the O of square root of n fit?
It's towards the top.
Okay, towards, oh yeah.
Before in.
Before
King
in?
in, log 2.
After or before log in?
After.
After. Yeah, because square root's going to grow a little faster than log, because it's really just into the 1/2. So that's going to be faster than log, but not as fast as linear. Okay, let me stop the recording and we'll go into doing some practice.